esta la última sesión del IWEX 2023. Tenemos hoy un grupo de presentaciones muy interesantes y para empezar tenemos la del doctor Francisco Cuevas Muñiz. El doctor Cuevas es egresado de la Universidad Autónoma de Querétaro, es doctor en Ingeniería, es miembro del SNI Nivel 1 desde 2015, tiene 3 estudiantes graduados de maestría y 2 doctorados en proceso. Cuenta con más de 25 artículos en revistas de arbitraje internacional y ha dirigido un proyecto con ACID AEM. Sus líneas de investigación son celdas microfluídicas de combustible y sensores de glucosa. El día de hoy nos va a hablar acerca de la aplicación de la microfluídica en sistemas de conversión de energía. Entonces, sea bienvenido, doctor. Muchas gracias por aceptar la invitación y, bueno, tiene la palabra.
Muchas gracias. Bueno, primero que nada quiero agradecer la invitación al evento. Me siento muy honrado de estar aquí. Y bueno, voy a hablar un poco acerca de lo que es la microfluídica y cómo la hemos aplicado para desarrollar sistemas de conversión de energía, ¿no? Principalmente celdas de combustible. Bueno, en nuestro trabajo lo que hemos realizado principalmente son microceldas de glucosa, etanol, metanol, y actualmente estamos incursionando en la generación de hidrógeno. La microfluídica, bueno, como su nombre lo dice, es el uso de fluidos que tengan dimensiones menores a una micra. Tiene bastantes aplicaciones debido a que en este rango de escalas los fluidos empiezan a tener comportamientos bastante interesantes. Principalmente la parte de la laminaridad, es decir, los flujos empiezan a ser más laminares, menos turbulentos, y esto empieza a evitar el mezclado de los fluidos. Por ejemplo, nosotros que trabajamos en celdas de combustible, las celdas de combustible a gran escala usan una membrana para evitar el mezclado del combustible con el oxidante. Cuando se trabaja con microescala, podemos prescindir de esa membrana, ya que los dos líquidos no se van a mezclar por la propiedad de laminaridad. Entonces, por ejemplo, aquí vemos un ejemplo donde tenemos un combustible y tenemos lo que es el oxidante, y vemos cómo en un principio no hay mezclado, conforme va avanzando a lo largo del canal se empieza a mezclar. Y aquí es donde nosotros tenemos que jugar con las propiedades de ancho de canal, velocidad del flujo y largo del canal para evitar lo menor posible este mezclado y evitar que el combustible llegue al cátodo o, en caso contrario, el oxidante al ánodo. En ese tipo de con celdas tenemos 2 reacciones, ¿no? Principalmente lo que es la del combustible, donde los más combustibles más usados usualmente son alcoholes. Se está empezando a usar otros tipos de combustibles, pero principalmente son alcoholes, etanol, metanol, glicerol, entre otros, por su alta densidad energética. Mientras que en el caso de oxidantes, pues se prefiere el oxígeno porque es abundante, es fácil de conseguir. Y pues al menos antes de la pandemia era bastante económico. Ahorita ya las cosas empezaron a cambiar. Pero bueno, finalmente la idea es usar oxígeno de este lado, que es preferible que usar otros oxidantes como por ejemplo, el peróxido de hidrógeno. Sin embargo, esta reacción tiene un problema. Como el oxígeno suele ser poco soluble en agua, nosotros podemos tener una concentración muy alta de combustible y una muy baja de oxígeno, lo que lleva a que si el combustible cruza la barrera y llega al cátodo, empieza a reaccionar preferentemente. Usualmente como cátodos se usan materiales pues catalizadores principalmente base platino. Y estos catalizadores reaccionan muy bien con los combustibles. Entonces nosotros nos pudimos ver que, bueno, al ser un problema esta reacción catódica, la consideramos como limitante y altamente susceptible al crossover, que es este efecto donde el combustible llega al cátodo. Entonces empezamos el desarrollo de materiales tolerantes, materiales que pudieran catalizar la reducción de oxígeno aún en presencia de combustible. Empezamos con materiales con platino y plata por reducción química, después por electrodepósitos, por deposición de láser. También probamos materiales enzimáticos y como combustibles glucosa, etanol y metanol. Este es el trabajo de varios años, no es un trabajo de una sola persona, es un trabajo que hemos tenido durante todos estos años. La síntesis química se realizó por una síntesis que es la síntesis de Brust. La modificamos un poco, la original era para oro, nosotros la hicimos con materiales bimetálicos, donde poníamos, por ejemplo, platino, plata, en cierta proporción, y obteníamos una nanopartícula mezclada. Lo interesante pasó cuando este material lo llevamos a calcinar, ya que para quitar la parte del tiol, que es el que queda aquí afuera, que es el que estabiliza la molécula, lo tuvimos que calcinar y descubrimos que el interior era de platino y el exterior era de plata, lo cual en principio podría sonar bastante mal, ya que siempre lo que queremos es tener platino afuera y en el interior el material de menor valor. Sin embargo, descubrimos que este material presentaba tolerancia a la reducción de oxígeno, a la oxidación de glucosa en presencia de oxígeno. Entonces, esto lo vimos, por ejemplo, aquí tenemos el platino, donde vemos que ya está, aquí de este lado está oxidando glucosa, mientras que el platino plata no está oxidando glucosa, solo está reduciendo oxígeno. Y esto fue en medio básico. Entonces ya nosotros, pues al hacerlo en celda de combustible, esta era nuestra primera celda que probamos. Esta celda se hizo por un método de prensado en acrílico, prensado en caliente. Y bueno, nosotros teníamos originalmente una entrada de combustible y una entrada de oxidante. Y al ver este nivel de tolerancia, nosotros propusimos pues usar un solo flujo. Entonces ahora cambiar la forma en que esto trabajaba y empezar a usar una solución mezclada. Observamos que con flujos separados pues obteníamos densidades de potencia de 400 microwatts por centímetro cuadrado, mientras que con el flujo mixto seguíamos obteniendo valores, pues en algunos casos hasta de 400. Entonces realmente no veíamos el efecto de tener glucosa en el lado catódico, lo que nos indicaba una alta tolerancia de este material. Entonces nosotros, pues indagando más en el sistema, ya esta fue la tesis de maestría de un estudiante, hicimos materiales capa sobre capa, es decir, depositamos platino y sobre él depositamos plata. Esto todavía es bastante polémico porque luego me dicen, pues es que eso no tiene sentido, ¿no? Usualmente funciona al revés. Sin embargo, lo hicimos por dos técnicas. Lo hicimos por cronoamperometría, donde primero depositábamos platino y después depositábamos la plata, que preferentemente se depositaba sobre el platino. Y tuvimos la oportunidad de hacer una estancia, bueno, el estudiante tuvo la oportunidad de ir al INRS en Canadá, en Quebec, donde pudo usar una técnica de PLD. Esto lo hizo con el doctor Mohamed Mohamedi. Y lo hicimos sobre papel toray. Lo primero fue sobre carbón vítreo, lo segundo fue sobre papel toray. Incluso se propuso una celda con una sola entrada y una sola salida. Y bueno, los resultados fueron bastante buenos. Observamos que seguía reduciendo oxígeno. Él lo hizo con metanol y también en medio básico, y seguía reduciendo preferentemente el oxígeno. Entonces, este diseño, donde vemos que además en el diseño anterior nosotros teníamos los electrodos en la pared, lo voy a regresar, aquí está. En la pared teníamos los depósitos, y en este diseño nosotros teníamos una celda donde pasaba a través del electrodo. Es un electrodo que ya aprovecha lo que es también el volumen del papel toray, que es un material poroso, pues fácilmente lo puede pasar el líquido. Y además esta celda incorporaba ventanas para tomar el oxígeno del aire. Entonces eso maximizaba la potencia obtenida, porque no era el que iba disuelto, sino lo tomaba del mismo aire, donde está más disponible. Y bueno, también podemos observar que estas son dos celdas, ¿no? Son dos celdas acopladas, que se pueden acoplar en serie o en paralelo, aumentando la potencia extraída. Esta celda creo que mide como 5 centímetros, algo así. O sea, no es muy grande realmente. Y bueno, eso, como les digo, lo hicimos hasta... En ese caso es por PLD. También le había hecho pruebas también con electrodepósitos y también han salido bastante prometedores. Actualmente estamos trabajando en la parte de generación de hidrógeno, donde, bueno, este es un estudiante de doctorado, que él hizo síntesis química de materiales de hidróxido de níquel, bueno, óxido de níquel y óxido de cobalto. Los estuvo haciendo combinaciones, donde él empezó a probar, bueno, la parte de la reducción de oxígeno, y estuvo ahí comparando varios materiales. Y también se propuso lo que es un electrolizador, también eso fue parte de su trabajo. Digo, él todavía no se titula, pero bueno, ya lleva trabajo avanzado, donde se propone una entrada de agua y una salida de oxígeno y una de hidrógeno. Y este es un video, no sé si se pueda reproducir. Ahí está. Entonces, no sé si se alcanza a ver. Pero bueno, aquí vemos la formación de burbujas, si alcanzan a notar. Este es en tiempo real. Obviamente la producción todavía es un poco lenta, pero bueno, estamos ahí haciendo avances, ¿no?, para mejorar la eficiencia del dispositivo. Y también pues es un dispositivo de tamaño muy pequeño, que pues ya tendría aplicaciones muy específicas, ¿no? No es ahora sí, para cualquier aplicación. En el caso de materiales enzimáticos, tuvimos el trabajo de doctorado de la doctora Berenice, que bueno, en este trabajo fue una colaboración más que nada, donde ella trabajó con materiales que eran a la casa, creo, y usábamos un material de oro para la oxidación de glucosa. Aquí la novedad consistía en usar un material, bueno, un combustible que era un líquido de cultivo celular. O sea, un cultivo celular gastado que ya sabía, que ya no servía, se podía incorporar dentro de una celda de combustible. Esto fue en colaboración con el CIMBESTAB de Monterrey, con el doctor García Cordero, y se diseñó lo que es esta celda de combustible que vemos aquí, donde teníamos, bueno, la entrada era del combustible, venía del dispositivo de cultivo celular, y creo que también tiene una ventana para el oxígeno. Igual eran electrodos porosos. Nosotros pudimos observar, se usó el material de oro también obtenido por la técnica de síntesis química, Se probó en medio alcalino, en medio neutro, donde observamos, bueno, ahí la reducción de la oxidación de la glucosa. Y se llegó a usar el medio del cultivo celular, que se llegó a usar varios días y también obtuvo ahí un buen rendimiento. Aquí se movieron las letras. Pero bueno, básicamente este es el diseño, ¿no? Con electrodos porosos. Igual hay por ahí, creo que tiene una ventana. Ah, sí, de hecho sí era un sistema air breathing. Y tenemos, bueno, aquí lo vemos que la potencia que llegó a obtener, que bueno, es baja, pero finalmente es un sistema que es una energía de reuso, ¿no? Un sistema de reuso. Entonces no estamos partiendo de glucosa pura, sino estamos partiendo de lo que quedó de glucosa. Y bueno, ahí más o menos una comparación con la literatura, vemos cuánto se llegó a producir. Y bueno, esto es la parte de la producción de energía. Es como le digo, un breve bosquejo de lo que estamos haciendo. Principalmente, pues como pueden ver, es más que nada el desarrollo de los materiales, de los electrodos, donde nosotros los fabricamos. Tenemos impresoras 3D, equipos de micromaquinado de CNC, y casi todo lo hacemos en acrílico, que también tiene la ventaja de ser transparente y nos permite ver lo que está ocurriendo dentro de los sistemas. Adicionalmente, como otra línea de investigación que también quería presentar, teníamos lo que son los sensores electroquímicos, donde nosotros también desarrollamos los materiales para la medición de diferentes sustancias. En este caso, bueno, sería glucosa lo que estaría presentando, que es el proyecto que tuvimos con la Agencia Espacial Mexicana. En este caso, bueno, nosotros nos salió de una inquietud con una convocatoria de la Agencia Espacial, allá en el 2015, y nosotros propusimos que debido a los cambios que ocurren en el cuerpo, en el organismo, al estar en condiciones de microgravedad, pues empieza a haber una redistribución de fluidos, donde tenemos como la sangre es empujada a la parte superior del cuerpo. Entonces nosotros, proponiendo un sistema microfluídico, pensábamos pues que se podría medir la glucosa, ¿no? Esto se hace con dispositivos tipo lab on a chip, donde nosotros incorporamos pues lo que es un material que sea capaz de detectar glucosa. Y bueno, se hicieron una serie de diseños, propusimos finalmente para tratar de evitar los efectos de la microgravedad de la distribución del fluido. Eso se hizo con cálculos con una microgravedad equivalente a la que está presente en la Luna, que obviamente es muy baja, pero realmente aún en la estación espacial no es tan baja. Llegamos a hacer pruebas en un sistema de microgravedad artificial. Tuvimos la oportunidad de ir a Lima, Perú, donde tienen este equipo, y nosotros vimos cómo cambia, ¿no? Cómo cambia del blanco, que vemos que es la glucosa en un caso de una muestra ideal, y vemos la sangre, ¿no? Que tiene un comportamiento similar. Entonces con eso concluimos que sí era posible llevar a cabo la medición. Y en este caso, bueno, no sé, este es el dispositivo ya armado, y bueno, estamos viendo que también el tamaño es otra vez cerca de 5 centímetros, creo, y 2 centímetros. Aquí tenemos la entrada, aquí tenemos la salida, tenemos un sistema de 3 electrodos. Y para ponerlo a prueba, nosotros tuvimos que introducir todo el sistema dentro de la máquina. Esta es una máquina de 3 marcos que están girando todo el tiempo. De esta forma compensa el efecto gravitatorio. y lo hace de una manera aleatoria para que no introducir otra fuerza, ¿no? Porque si no, entonces ya no estamos viendo microgravedad, sino estamos viendo otra fuerza diferente. Durante este proyecto se incorporaron varios estudiantes y tuvimos la oportunidad de trabajar con diferentes grupos a lo largo de todo este proyecto. Y bueno, como les comentaba, este es un proyecto que fue apoyado por la Agencia Espacial, que logramos exitosamente llevar a cabo. No lo tengo aquí, pero actualmente también estamos trabajando en la parte de detección de glifosato. Esta se hace con polímeros de impresión molecular y con un sistema que es impedimétrico, que es un sistema que a través de la impedancia nosotros vamos midiendo los cambios, ¿no?, del polímero, y pues vamos correlacionando con las concentraciones. Y esto también es un sistema a pequeña escala, apenas tenemos ahí avances también muy interesantes, parte del proyecto de un estudiante de doctorado. Y bueno, eso es ya es otro trabajo aparte, ¿no? Creo que me sobró mucho tiempo. Me fui más rápido de lo que pensé. En mi cabeza iba a durar más tiempo. Sí, claro, no hay ningún problema.
Muchísimas gracias, doctor. Bueno, muchas gracias. La audiencia, por favor, si tiene alguna pregunta.
Sí, se escucha, ¿no? Buenos días, doctor. Reiterarle las gracias por la presentación. Realmente mi duda es un poco puntual. Yo quería saber acerca de, un poco más, si pudiera abordar acerca de los dispositivos Lab on a Chip. Sobre todo que usted presenta, que está relacionado con un medio de cultivo celular. O sea, creo que nunca había escuchado un dispositivo de este tipo. Por lo menos no me dedico a esta área. Entonces, que nos explicara un poquito más qué significa esta tecnología, o sea, el término a qué hace alusión, si tipo de dispositivos, si hay varios dispositivos de este tipo o solo los dispositivos Lab on a Chip están vinculados con los medios de cultivo. Y en este caso, ¿cómo este dispositivo puede utilizarse como combustible de glucosa? O sea, si pudiera abordar, por favor, un poco más este tema, se lo agradecería.
Claro, bueno, voy a intentar ahora sí que aclarar lo más posible. Los dispositivos Lab on a Chip, básicamente, lo que hacen es llevar a cabo lo que es todo el proceso de laboratorio, ¿no? O sea, creo que tenía la imagen, pero creo que la tenía acá, ¿no? A ver. Así, aquí está. Entonces, su nombre lo dice, ¿no? Lab, o sea, un laboratorio en un chip. Es como imaginar todas las operaciones que ocurren en un laboratorio, pero trasladarlo a una escala muy pequeña. Entonces, en este chip la idea es meter una muestra. Yo les doy el ejemplo más clásico que casi todos lo conocemos, que son los glucómetros. Nosotros en el glucómetro tomamos una gota de sangre y no le hacemos nada realmente. O sea, la gota de sangre va directo a la tira y obtenemos una medición. Entonces, ¿cómo ocurre esto? Bueno, simplemente que cuando la gota entra dentro de ese huequito que tenemos ahí en la tirita, ocurren todas las reacciones que tienen que ocurrir, que es principalmente un acoplamiento con una enzima, una producción de electrones, y esos se van a un circuito eléctrico y el aparato ya nos dice cuánta corriente o cuánto potencial se produjo. Digo, en algunos casos, en otros tenemos el caso de que sea por una determinación óptica. Entonces, toda esa operación ocurre ahí adentro. Entonces, llegamos al nivel en que una persona sin menor conocimiento, o sea, más que saber cómo prender el aparato y cómo tomar la muestra, lo puede llevar a cabo, ¿no? Entonces, eso es una especie de lab on a chip, es un lab on a chip, de hecho es un point of care, también le llaman. Entonces, la idea es, ¿cómo podemos simplificar todo esto, no? Hay muchos lab on a chip, se están desarrollando cada vez más y ahora con las enfermedades, por ejemplo el COVID, se empezaron a trabajar también muchos lab on a chip para detección de COVID, donde nosotros dijéramos, bueno, pongo una muestra, puede ser a lo mejor de saliva o de algún fluido, y voy a detectar la presencia o la ausencia de este virus, ¿no? Se colocaba algún tipo de, en algunos casos, alguna cadena de RNA que fuera complementaria y detectara, ¿no? Eso es principalmente lo que ocurría, ¿no? Entonces la idea era hacerlo lo más pequeño posible también para consumir la menor cantidad de muestra, generar el menor residuo y no tener pues un problema de contaminación, ¿no? De tener un exceso de reactivo o de tiritas o de chips, ¿no? Y también pues para hacerlo barato, ¿no? Entonces, principalmente el uso del lab on a chip son esos, son más que nada detección de alguna especie de interés. Pero pues podemos pensar en que podemos detectar desde alguna molécula, como puede ser un contaminante, puede ser algún o incluso a lo mejor algo que a alguien le interese mucho, ¿no? Si quieres detectar, no sé, por ejemplo, vainillina en vainilla, o si quieres detectar alcohol en tequila, por ejemplo, y alguien quiere hacer un lab on a chip, para eso se puede hacer. O una enfermedad, como decíamos, en el caso de COVID o en el caso de cáncer, incluso se están trabajando lab on a chips para cáncer. Y también tenemos el caso de también para moléculas de interés, como de interés, ¿cómo decirlo? Pues de interés para la vida, ¿no? Como el caso de la glucosa, urea, lactosa o algún precursor o algo que incluso hay gente que está trabajando en estos de los neurotransmisores, para detección de neurotransmisores. Y pues básicamente lo que hay que tener es la molécula complementaria, o sea, qué es lo que va a ayudar a detectar, ¿no? En el caso del trabajo que se hizo con el doctor García Cordero, sinceramente no sé para qué usaban ellos ese lab on a chip. Ese es trabajo de ellos. Nosotros nada más nos dijeron, bueno, nosotros usamos este chip y es un cultivo rico en glucosa porque el objetivo era crecer esa célula, ¿no? Entonces, pues nosotros lo que hicimos fue tomar ese residuo. Dijimos, bueno, ese residuo tiene glucosa, seguramente le quedó algo porque no se gastó toda, y pues reusarla, ¿no? Como una segunda fuente de alimentación, un reactivo gastado. Y pues en este caso sí se vio. Seguramente aquí, bueno, lo que hacía era colocar, crecer células y contarlas, ¿no? Y contar a lo mejor la presencia o ausencia de ellas. Pero en este caso sí desconocería cómo, más bien el propósito de este dispositivo. Pero básicamente ese es un bosquejo. No sé si ayudé a clarificar o quedaron algunas dudas.
Bueno, es que a priori, mirando este tipo de dispositivos, uno lo que se le pasa por la mente es que se utilice más bien como una especie de biosensor o algo así. Pero en este caso se está utilizando como fuente de combustible, como una seta de combustible, ¿no? Entonces, sí lo veo un poco, sí lo veo bastante interesante y como que para mí es algo nuevo, ¿no? Entonces, por eso la pregunta.
Sí, la parte del lab on a chip es para detección. Pero nosotros dijimos, bueno, si esto se puede reusar, a lo mejor puede ser una energía extra, ¿no? Y a lo mejor lo que sobre esto, en algún momento podría alimentar al dispositivo original. Eso era una posibilidad, ¿no? Que nosotros pensamos que se podría hacer. Entonces a lo mejor estamos hablando de que imagínate un dispositivo que en vez de que tuviera una batería se alimentara a sí mismo. Esa sería una posibilidad, porque los glucómetros o todos estos sensores pues tienen baterías, ¿no? Que son las que lo alimentan. Entonces, o a lo mejor si no prescindir al 100%, pero al menos a lo mejor gastar menos energía, como una especie de recuperación, ¿no? Un sistema de recuperación energética que permita reducir el consumo. Y pues a la larga obviamente esto generaría pues un ahorro. Entonces, eso es lo que, más que nada, esa era la idea, ¿no? O sea, adaptar esto a un lab on a chip. En el otro caso sí era ya propiamente un lab on a chip.
Gracias, doctor. Muy interesante la plática.
Gracias por la pregunta.
Sí, doctor, me surge una duda porque, o sea, son varios proyectos los que presenta, muy interesantes todos. Entonces, si usted tuviera que apostar por uno de ellos, ¿cuál cree que tenga más posibilidades de llegar a un dispositivo funcional o tal vez comercializable? ¿Qué opina usted?
Uy, esa es una pregunta difícil.
Yo sé.
Sí, vamos, bueno, la idea es atacar diferentes problemas. Como te digo, no es un trabajo de un año, ni es trabajo que se está haciendo ahorita todo. Ahorita estamos principalmente en la parte de glifosato y en la parte de hidrógeno. Por ejemplo, el glifosato, que no lo presento, pero es un problema actual. Actualmente ya existe regulación, ya se está prohibiendo la importación de glifosato, pero pues el glifosato es persistente, entonces va a seguir otro rato ahí, por lo menos unos 5 o 10 años, acompañándonos en las diferentes muestras de tierra o agua, y eso va a ser va a seguir siendo un problema. Entonces obviamente creo que es un problema que nos va a seguir ocurriendo. Por ejemplo, la generación de hidrógeno pues también podría ser algo interesante. Lo que ahí sí nos hace falta mucho es afinar todavía la tecnología. En el caso de glucosa, también uno de los comentarios muy recurrentes es, pues todo el mundo está haciendo glucosa, todo el mundo está, ¿qué tanto se puede innovar en glucosa? Pero nosotros creemos que sí se puede innovar, y México, siendo un país que tiene un alto índice de diabetes, aún así tenemos mucho trabajo por hacer en esta área. Y además es un trabajo que nos permite ir abriendo otras líneas, ¿no? O sea, quedaron varias líneas por abrir ahí, que desgraciadamente pues por falta de recursos, falta de gente y de tiempo, pues no se ha podido terminar. Pero se generaron varias ideas. Y en la parte de combustibles, pues a lo mejor todavía también es como que pensar en escalas pequeñas todavía no se nos da. Pensamos en energías alternativas cuando vemos carros autónomos, bueno, carros de hidrógeno, carros de eléctricos o sistemas muy grandes, ¿no? Pero a microescala todavía no lo visualizamos. Entonces ahí yo creo que todavía falta más trabajo en esa parte. Entonces parece que si tuviera que poner mi dinero en algo, yo creo que me quedo pues con la parte un poco de glifosato, que es lo más actual ahorita, y la parte de hidrógeno, que yo creo que sí. Pero sí es difícil escoger, porque la idea es justamente ir abriendo líneas, ¿no?
Claro. Ok, muchas gracias, doctor. Sí, ¿alguien más tiene una pregunta?
Muchas gracias, doctor. Está on, bien. Gracias, sí. ¿Usted conoce alguna tecnología ya que se comercialice sobre, digamos, microfluídica para alguna tecnología de conversión de energía, digamos, producción de hidrógeno, que esté comercial ya?
No conozco en este momento alguna.
Porque a veces también cuando vemos a alguien, la gente siempre está buscando oportunidades,
Sí, claro.
para hacer negocio. Y entonces siempre con un semáforo que pone una luz verde en una dirección, es ver si tenemos alguna tecnología ya comercial. Por eso era mi pregunta, porque eso nos podría servir como semáforo, es decir, por aquí, por este camino podemos pasar.
Sí, claro.
Uh-huh. Bueno, tecnologías comerciales, el Apple Chip, eso sí ya hay muchas, ¿no?
Sí.
Sí, eso sí, por supuesto, sobre todo en bioquímica clínica, en ese tipo de cosas, ¿no? Pero me refería en particular al caso de energía. Muchas gracias.
Buenos días, doctor. Excelente presentación. Mi pregunta es respecto al proceso o al equipo con el cual se logró la unión de plata sobre platino. Me lo podría, no sé si aclarar un poco o ver el equipo, el proceso con el que lo lograron, porque eso es pues realmente nuevo para mí. Como usted lo menciona, no es común, ¿verdad? Entonces yo sí quisiera ver cómo es esa parte.
Bueno, el trabajo
esa unidad?
original,
Gracias.
más que nada, era hacer una síntesis química, donde nosotros colocábamos una sal de platino y una sal de plata. Entonces, reducíamos químicamente con, ¿qué es? Bromuro de tetraoctilamonio, y con como ya tiene rato que la hice, creo que era boridruro de sodio, sí es boridruro de sodio, aquí está. Entonces, en esta solución, bueno, se reduce y se obtenían pues las nanopartículas, ¿no? Suspendidas ahí en la solución con recubiertas con tiol. Estas después nosotros las calcinamos, o sea, el proceso es una reacción química, se calcinaba al día siguiente, el proceso de 2 días, después de varios lavados se calcinaba a 400 grados, y ahí era donde empezó a ocurrir las situaciones extrañas. Nosotros calcinábamos, sacábamos la muestra, pues pensábamos que teníamos una mezcla, ¿no? Entonces empezamos a hacer las pruebas y empezamos a ver que esto era tolerante al combustible, ¿no? Después, cuando ya hicimos los análisis de TEM, pues ya vimos que era un core shell, que teníamos un core shell. Incluso hay un trabajo de una simulación que se hizo una simulación por computadora con un grupo de la UNAM allá en Querétaro, y ellos corroboraron que el proceso efectivamente daba una core shell de platino adentro y plata afuera, por medio de FT. Por medio de FT ellos comprobaron que eso también estaba ocurriendo. Nosotros, bueno, pues sí estábamos sorprendidos porque usualmente el catalizador se queda afuera, o sea, el platino, ¿no? Pero nosotros creemos que como el platino es reactivo al combustible, que en este caso era glucosa, y reactivo al oxígeno, lo que hacía la plata era un efecto de protección. Entonces, al ser la molécula de glucosa más grande, bueno, una posibilidad era que se formara algún tipo de poro o algún tipo de interacción que evitara que reaccionara con la glucosa y dejara que solo reaccionara con el oxígeno. Entonces, es como ese recubrimiento le daba esa propiedad al platino. Entonces ya después nosotros, pues más avanzados, lo que hicimos fue hacerlo pues ahora capa sobre capa. O sea, ahora ya no era una nanopartícula, sino era un depósito, ¿no? Una película. Entonces colocamos una película de platino sobre carbón vítreo por vía electroquímica, una cronoamperometría, y después depositábamos plata. Y el efecto se volvía a ver. Entonces era un efecto repetitivo. Veíamos que efectivamente este material seguía siendo tolerante en este caso era metanol y también a etanol. Entonces vimos que realmente sí le estaba confiriendo alguna propiedad de ese recubrimiento de plata. Y después tuvimos la oportunidad de hacerlo por depositación láser, que es un equipo muy especializado, ya es un equipo muy caro, que está allá, lo tienen allá en Canadá. Obviamente pues esto no era con el objetivo de hacerlo comercial, pero era tiene un control mayor sobre el tamaño de la película. Y entonces se hicieron depósitos a diferentes pulsos, se controló los espesores y se volvió a observar lo mismo. La presencia de plata generaba esta protección que evitaba la oxidación del etanol. Entonces, pues nosotros concluimos que efectivamente hay un efecto cuando el platino es recubierto con la plata. No hemos podido ver si con otros materiales ocurra, con otros en vez de plata, a lo mejor coloca otro material, pero pues podría ser una posibilidad, ¿no? Que a lo mejor que el adicionar un segundo material pues cambia las propiedades del primero, ¿no? Del inferior. Entonces eso fue lo que nosotros logramos observar.
Por último, la aplicación de ese recubrimiento en el área médica, no sé si me quedó claro.
¿En el área médica?
No sé, es la pregunta.
Bueno, en el área
La
médica se
aplicación.
sabe que la plata es
Pero el platino.
Antibacterial, el platino, no sé si tenga aplicación en
Sí,
medicina.
para hacer catéter de ¿cómo se llama? Diálisis,
Ah, ok.
son
Pu-
de platino.
Pues a lo mejor lo que se podría hacer es
Con-
como la plata es
sí.
antibacterial, ¿no? Podría servir como a lo mejor una barrera para evitar alguna contaminación. Se me ocurre que a lo mejor podría ayudar en eso. Pero la verdad no se me había ocurrido.
Sí, me imagino. Gracias, doctor. Muy
Sí,
amable.
gracias.
¿Alguna otra pregunta? Sí.
Buenos días, doctor. Muchas gracias por su presentación. Yo quiero preguntarle un poquito, bueno, ya contestó, eso porque usted habló que esta parte de depositar platino y luego plata es un poquito polémica. ¿Ustedes qué hipótesis formularon en su artículo para explicar por qué funciona?
Nosotros vamos sobre dos líneas, ¿no? La posibilidad de que haya una porosidad ahí, a lo mejor muy, muy pequeña, que no hemos detectado, y que ese tamaño de poro evita que la glucosa o el metanol, al ser moléculas más grandes que el oxígeno, pues no puedan entrar, ¿no? Bueno, el metanol no tanto, pero el etanol sí. La otra posibilidad es que ya a nivel energético, pues se estén combinando, ¿no? Que haya una especie de combinación energética, pero pues obviamente eso requiere más estudios, más análisis ya de parte, ahora sí, de expertos en esta área, y pensar que a lo mejor energéticamente al combinarse, pues se está favoreciendo una reacción sobre la otra. Que digamos que el platino que está expuesto le confiere propiedades a la plata, ¿no? Que es la que está afuera. Entonces, esas son nuestras dos posibles teorías de lo que está ocurriendo.
Okay. Y la siguiente pregunta va un poquito más a su proyecto de detección de glifosato. ¿Ya tienen ustedes algún avance como para poder usarlo para una aplicación en otro proyecto distinto? O sea, digamos, ya ustedes tendrán una aplicación de detección de glifosato.
Ya hemos detectado glifosato, ya estamos así que determinando en qué niveles, y lo que hace falta todavía son pruebas de selectividad. Pero ya estamos, digamos que sí ya tiene un avance considerable.
Muchas gracias, doctor.
¿Tienen alguna otra pregunta? Yo creo que ya eso sería todo. Muchísimas gracias, doctor. Gracias por su presentación y su tiempo. Por favor, un aplauso.
Gracias a ustedes.
Y bueno, ahora los invitamos a pasar a un coffee break para después continuar con la próxima conferencia. Gracias.
me?
Good afternoon, Professor Giorgetti. Can you hear me?
Yes.
Can you
Hi,
see
how
me?
are you? Yes.
Hi. I am fine. How are you?
Fine,
Fine, thank you. Sounds good.
Okay, so it seems that you're almost lunchtime there, but I almost, to the evening, and then, okay, it's 6 o'clock here, 10 a.m. In Mexico, right?
That's right. Está dispuesto.
Hello, everyone. Do you hear me?
Yeah.
Hi, doctor, Professor Marcos.
Ah, how are you?
Fine, and you?
Hey, I'm fine, Edilso. So I'm very pleased to be here anyway.
Okay, welcome.
I heard that you're gonna hear me anyway. Okay, so I see the room is. I saw the room now.
Yeah, many young people are welcome you to hear your lecture.
Okay. Yes, of course.
Spectroscopy, electrochemistry, and energy, S2C, at the University of Bologna. His research interest covers the field of structural and electronic characterization of materials and solutions by core-level spectroscopies, such as X-ray spectroscopies, the applied electrochemistry, sensors, the synthesis and characterization of materials for advanced batteries. He has applied Prussian blue-based materials in potentiometric and amperometric sensors, ion exchange, batteries, and so on. He's expert in methodologies for data analysis. He had pioneered the in situ characterization of energy material by the X-ray absorption synchrotron radiation technique. He has coordinated more than 30 projects in synchrotron radiation facilities. Professor Marco Giorgetti, welcome to our EWEX 2023. The word is yours.
Okay. Thanks a lot for a very kind presentation. I'm really glad to be there, okay, to be here and there, let's say. And so it was very a pleasure because as a first, it's very nice that, people in different continents can be also in contact with this kind of the technology that we have now. This is at first. The second, I was very pleased to be invited by Professor Edilso Reguera, because when I started to work with as a son of arrays, it's come up this name all the time, and it was. I'm really glad now that it's really the occasion to see him, and then and we'll be very glad if we can. Start this kind of a collaboration or something like this. It was interesting because any time that we, had popped up to a single and a different meta-hexacyanoferritic compounds, he was the one that already, studied the structure, some properties, and that was very useful for the work, to my work, to the work of my students now. And I think also in Europe, there were some other people that can, of course, thanks him for all of this research that is done, since many years. Okay, so thanks for the presentation. Then I'm going to my talk today, and we will cover one aspect of the material science. This is the battery material, and especially the characterization of battery material with especially the active material that we have inside the battery with the use of X-rays. I will show some emphasis in pressure blue-like material, of course. And then, but first, let's see where we are located. Here in Mexico, Europe, and Italy here. And then there is a region called Emilia-Romagna, and then the Bologna is the capital of that region, just in the middle up center of the Italy. Bologna, let's say, it's a nice city in the middle of the Italy. And this is an aerial view of Bologna. And you can also, is called the Learn because of the old university, and also the fat because of this food tradition. This is also has been from the UNESCO a great city of the music, and you may see from the aerial view that is one of the largest and the most well-preserved medieval historic center. Let's say if you got the chance, of course, I'm inviting you, any of you, if you to come visit Italy, and then you have to stop to Bologna. And I have another couple of pictures just to go in a good mood for the presentation. And the first is this one, what is famous for Bologna. You have these porticos. Okay, what's the matter? What do we have these porticos? Basically, you have this walkway that's connected all the city center that we saw there. So, for instance, the students enjoy a lot because they never got wet during, winter time when it's raining or when it is snowing. Another piece that you want to, Bologna is famous for its kind of food tradition, as I said. And I don't know if you are aware, but as part of some vegetables and fruit, there is a lot of, let's say, salami, different types of salami, mortadella. And probably Bologna is famous for these tortellini. And here indicated the tortellini and also the tagliatelle. Okay, so Matt, we are here to talk about science, right? And so science, we can start to state some of the important fundamental problems that we have in when we build it up, when you want to, let's say, also put together some elements, some materials, active materials of both sides, cathodic sides, and also the negative sides. But then, of course, we are interested to study some Faradaic process in batteries. So this is called for some fundamental open questions. So on one hand, you have all the electrochemical characterization that typically we perform on a lot of laboratories and perform. Okay, and on the other hand, you have this characterization that is structural characterization, but also structural characterization and also electronic characterization. So this is very simplified scheme that everyone knows. So we have a current collector on both sides, on the positive electron, the negative electrodes. This is a very simplified, for instance, is graphite on the negative electrodes, and this kind of layered samples on the positive electrodes. Some balls here indicates the ions that the course is going between the two parts. So the two components, the positive electron, the negative electron. So the shuffling on one side and the other side during charge, during discharge. Of course, ion can be lithium, can be sodium, can be also now some other elements, because some other elements are in the studies. I'm sorry, I have a, okay. No, okay. And of course, the electrolyte. The electrolyte can be liquid electrolyte, can be solid electrolyte, can be water electrolyte, okay? So which are the fundamental open questions that want to come here? So first of all, where does the charge go on the electrode, the positive electron, and when the charge go on the negative electrodes? We can, if you think of this structure to be a layered one of the possibility could be V2O5, that is layered samples. So the simplified electrochemical reactions are written. So vanadium 205 takes X lithium takes electrons, and it go to the charge, to this charged one. where is the lithium sample. So where does this lithium go, and especially where does the electron go? Are there any possibility to check effectively where they go? I mean, for the both on both sides. The same applies to the negative electrons. Okay, so we have also charge and discharge in here. So if now one of the most performing cathode material, but also in anode, I could say, they are metals. Of course, we need to have a very specific in which kind of metal is going to be oxidized, reduced, and probably we need what we might call very sensitive, very special techniques, and the sensitive techniques for the atomic species. And that's why probably one of the most interesting choice is to use in X-rays. Why is X-rays? Because they are a strong selectivity for the atomic species, as we well know. X-rays also can be used not only for having this structural characterization by some exotic techniques such as the X-ray atom spectroscopy they are going to talk about today, but also if you talk about the wavelength of the X-rays. X-rays stands from it's a center at about 1 angstrom. Could be 0.01 angstrom at the maximum of 100 angstrom. It's very, very large range, and it's interesting that if it's centered at about 1 angstrom, this means they are in the atomic dimension. So they know so well that is a very specific case in which the scattering from the atoms and the scattering from the electrons around the atoms, they are very, very important. It calls for another very interesting techniques. But I want to point out a couple of things in here. Of course, it's not a lecture of history today, but since we want to like to knowledge who the first observed the X-rays, and there are a few very interesting things about this guy, Wilhelm von der Röntgen, who first discovered the X-rays in this night, November 8, 1895, because that is an aerial view of his laboratory of Würzburg that was in Bavaria, in Germany. And so he had a couple of specialties. One is high voltage, low pressure. Why was the one that was able to observe X-rays on that night? It's interesting to note that there are a few things. The first, when you adopt high voltage, low pressure, we know now that by using high voltage, low pressure, he had a good chance for developing of X-rays, even in a sensitive cathode that he used for his for the machine for producing X-rays. The second, he was using a certain type of very specific type of detector, platinum baryocyanate, and it was let's say glowing green. And the funny thing is that it was eye blinded, on the color blinded, and so he had a very specific. He was able to see very specifically, and especially to catch any kind of even low concentration of a green. So it was the one that at a certain point, at a certain period of time, November 8, 1985, was the only one that you might have seen that X-rays. Okay, so this is just to have a funny moment. And that he was awarded Nobel Prize in Physics. That was the first one in 1901. Okay, why so important the use of X-rays in material science? It can be seen from this graph that the energy associated to this beam are enough to dislodge, to eject inner core electron, are different from optical electrons. Of course, here the architectural atoms, we have optical electron here we have core electrons. And the photoelectric absorption generated is the X-ray absorption generated these photoelectrons, which is also governed by a certain wavelength that here indicated. This is basically the conservation of the energy. So this is the K, the wave vector of this photoelectron. We will see that this play a very key role on the X-ray phenomenon. Okay, so when you create the core hole, that is the process, of course, then the process is very unstable. So we know that we have a couple of very interesting phenomena that also you know well. One is the X-ray fluorescence, because this atom is very stable. And the other is the Auger, from the French name of first observed the phenomenon. So they are called Auger electrons. Basically, here we have that this vacancy here is filled by some electrons from above. Then we have the simultaneous emission of some K alpha or the K beta. For instance, we know the copper K alpha radiation is one of the very important one, because a lot of X-ray machine around the world is made and generated by this K alpha radiation. And the second possibility is, the Auger electron, where this energy gap here is used actually to promote another electron from L states to the continuous well. So basically, we can measure, you know, that when we measure the kinetic energy of these photoelectrons, we open up all the family of techniques that is called, photoemission spectroscopy. But what is now comes, what is the main theme today, and basically on the X-ray matter interaction, when we bombard the X-ray with the material, of course, you have several phenomenon. So the mean transmitted, then we have what is very known is the scattered X-rays. So the coherent scattered X-rays is what we call, of course, a diffraction experiment. We call about, and we already said about X-ray fluorescence, but still this is also another very interesting analytical techniques. We saw one type of electrons, but actually there are two kinds of electrons. One is you bombard directly an X-ray with the material. So you have a photoemission, and then this is called XPS, X-ray photoelectron spectroscopy, or ESCA, electrospectroscopy of chemical application, of course, production of heat. Anyway, in the talk today, I will just talking about those two. The one is just, I want to measure how much of that energy X-rays have been absorbed by a given material. This is called X-ray absorption spectroscopy, and typically measure in a transmission modality, as here indicated. And the second, of course, is the X-ray diffraction experiment that anyway, is more traditional techniques for the determination of the crystalline structure and also the power diffraction experiment as well. Well, so, and since you want to talk about batteries and the use of the batteries to try to answer those fundamental questions, I prepare here a couple of slides, one for each of the techniques that we are going to do today to see. One is the use of X-ray diffraction for battery materials. That is basically we probe the long-range order. So it's the longer order that is probed with the X-ray, the X-ray diffraction. And in a battery operation, it's very interesting because we can do, of course, a phase identification, how much the phase modified within operando conditions, for instance. And if you have a very good crystallinity, we can also have a lattice defect, intercalation sites, and also open up to have this for in situ operando experiment. I will not talk about operando experiment they can do in a lab. I will just provide a few examples of the use of XRD using the sequential radiation, but try to highlight which is the benefits of using these techniques even at synchrotron, even though, of course, it's widely available to the lab. Okay, so the second is XAS, X-ray absorption spectroscopy on battery material. So they are complementary in terms, because here we probe the short range order of the metallic site. So first of all, we have to have metals that we want to check, because first we have to create that core hole that was, and to create this photoelectron on the core hole. So we have a metal, we create more core hole in that metal, and we're going to see what is looking around of only that metal. But this is interesting in batteries material because first, this is called element selectivity. If you have more than one metals, as in the case of metal hydroxyanoferrates, as you know so well, iron, and then maybe some other one, copper, cobalt, and whatever. So you have a double probe. You can just tune your X-ray beam on one core, to put your X beam in another core, and to see what is looking around. So this is element selectivity. It provides some chemical and structure information. It's a short range order, and this is something that, of course, we have to be well in mind, because we can see probably atoms at around 4 or 5 angstrom. And we see in the case of metal hydroxyanoferrates, this is actually range is kind of extended more than that because of particular cases that is called focus and superfocuses that allow to have this very intense scattering from atoms that are just behind and in between. Another very important fact is the crystallinity is not required. So as long as you have a battery material, of course, you start from a crystalline material, and then we have a kind of amorphization. This technique is still suitable to check and on whether you have a structural electronic modification upon the charge and discharge of the batteries. And also we show some in situ and operando experiment as an example. And finally, I will just dedicate a few times on what is the very advanced algorithm to do the analysis that is based on multi-curve resolution analysis. Okay, but we have to start with the figure that we've seen here. So it's a beam transmitted. So if we put our sample X, this is the thickness of our sample, basically, and our experiment is just to measure what is the absorption coefficient behavior as a function of the energy. What is the absorption coefficient behavior? If you think that is very analogous to the absorptivity that you have in UV visible spectroscopy, the K law is exactly the same because it's a power law, like here indicated. There we have E, here we have μ, mass absorption coefficient. There has actually a couple of contributions. One is the main and the most important one, because this is related to the absorption process that you first described, the creation of the core hole, plus you have the scattering that could be inelastic. But let's say, for all the first transition metal, okay, so they're very interesting for us. What the most contributing one is just the photoelectric portion or the mass absorption coefficient. So, said that, what is the SAS? SAS is basically as a measure of the absorption coefficient as a function of the energy. And you are going to see now one one experiment. And so basically we have this rising up feature here as a function of the energy. Here we created a core hole. And the plus, instead of having like a linear behavior, you have a lot of features here. Those features that are very interesting for us. And we can divide in 3 main regions, even though here we created the photoelectron. The Xenes region is the one from, let's say, this point to this point is around 50, 60, 70 electron volt on the edge. And basically, this is governed by electronic transitions. So if you're interested in giving information on the transitions, and especially oxidation states modifications, that region that you have to look at that. And yeah, also some of a very interesting region that is called pre-edge. This pre-edge is also electronic transitions, but they are transition from one s electron basically to bond states. Of course, they are free bond states. They are also very interesting because it is allowed to have calculations on the, for instance, on the first transition law metals. You can do some calculations about on the heterohedral field, which is the difference, for instance, between the T2G, EG molecular orbital and atomic orbital, and so on. And what is also interesting, the feature is this kind of oscillations. Why do we have these oscillations? We have oscillation because basically we have an atom to which we create a core hole, and they are surrounded we have some other portion of atomic sites. So we have another atomic sites, some other atoms. So atom coordinates can give these excess oscillations. They are called extended exorbitant fine structure, and they are due to photoelectron single scattering and multiple scattering. The photoelectron, which is one? The one they are created by bombarding with X-rays of the material. So basically, three regions. One is more for, let's say, electronic information, the other for structure information. Okay. And just to try to convince you of the fact that oscillations are related to the presence of coordinated atoms, one of the characteristics, let's say, of the previous was those oscillations, and they are present only in case of coordinated atom. So if this is the atom where you're going to create the core hole, this is the waves of the photoelectrons. You can see that photoelectrons can go out of the atom, then can just have a interference with some atoms that are just behind, and this is produce some informations on the oscillations that you're going to measure here. If you have just a single atom, as this one, you have just here monotonic decrease of the mass absorption coefficient of Thomson energy without oscillations. So that's the proof, experimental proofs that oscillation happens only with the coordinated atom. And of course, there are a way in which you can analyze those oscillations we see in a sample, and especially because the fact of on the metal as a sign of rays help us a lot, help me, for instance, a lot in the my work. And saneness. Okay, so we said that you have information, electronic informations. Which kind of electronic information normally you can get? So the easiest thing is to measure shifts. If you start from this, you measure oxidation, this goes completely to the right side. For that, actually, this goes to the other side. So, and we can just mention that there's a lot of literature about that. So basically, high energy transition is expected with the high valence state. So this is something that you can use in operand experiment, not only, but also if you don't have a clue about the oxidation states of some minerals or something, powders that you prepared, this is also a good way to measure oxidation states, okay, of your sample. And another fact that is important with excess that is dependent on bulk is a bulk technique. So all bulk volume of the material is concerned, not only the surface. Okay, now I want to stress one fact, the selectivity of the atomic species for the X-rays. So why do you want to use X-rays and not other beam? Because of course, we have a strong selectivity for the atomic species. So there is no ambiguity. When you bombard with a given energy, we know that we are going to see only what's up around that metal site, and that's it. So use X-rays guarantees a fantastic selectivity for the atomic species. Any metal of given material can be selected, and it's possible to focus on different metals. Just to tell you just the difference, pick up, for instance, manganese on iron, okay, or iron, the cobalt. They are at Z plus 1, Z plus 2. So the edge energy, I mean the energy that is necessary to eject one s core electron from manganese, iron, the cobalt, they are really large in difference. The manganese, that energy is 65, 31, 39 electron volt. For the iron, 71.2 electron volts. So there's, apart, they are fall apart like 600 electron volts. 600 electron volts is enormous quantity of energy. Just to mention, the red radiation on the visible light is 1 electron volt. The green radiation is a 2.5, and the blue radiation is a 3 electron volt. So you can see that, the panorama, the framework when you want to use those techniques is very precise, okay? So it guarantees a strong selectivity. Now comes just, I want to display an example. Anche we take advantage of such signature in the K absorption of metals. here just indicate an example of the analysis. It seems to be complicated, but anyway, this is the oscillations. They, of course, have been treated in several ways, but they are oscillations. And the main philosophy behind that is that if each fragment of atom that is around can contribute to the overall picture. And so this can be done by inverting information from the frequency to the distance. Of course, we adopt one operator that is called Fourier transformation. It's kind of similar to the phase prompt that we have in X-ray diffraction. And so we adopt exactly the Fourier transform. And in fact, if you Fourier transform the signal, we obtain in the signal domain this kind of behavior. The Fourier transform magnitude is a sort of radial distribution function around the selected atom. So 0 here indicates which metal we bombarded at that given energy was copper. Okay, so copper has one nitrogen here, another nitrogen here, couple of carbon here. So we expect to have 1, 2, 3 peaks. So, and this is what we can do and what is possible to do with analysis. Which kind of information they can release? They release information, especially on structural information, I mean, bond lengths and the coordination numbers around the selected atom. You can see from here that even from this fragment, the formations extend at maximum at about, like say, on the 4 angstrom or something like this. No more than that, because we just have to keep in mind this is a technique that is probably just the local coordination geometry. One of the, let's say, issue or negative point is that in order to obtain a good signal-to-noise ratio, in excess experiment, the use of synchrotron radiation is required. And of course, the source is not widely available. This is, for instance, another view of the synchrotron radiation that we have in Electra, in the Trieste, and where several beamlines are making upgrade in order to facilitate application also in the energy material field. So now, so far, and he will have, for instance, in November, a day dedicated just to all the users that have been involved in research on during battery material. And the XAS beamline is the one that probably I normally use for doing this research. And now you're going to see some other examples. The first is experiment. Of course, you were interested in experiment. So how is possible to do and to measure those spectra? And which kind of experiment can be done in batteries? And especially, what is the difference between the two words that normally pop up in the article, ex situ or in situ? Now also operando measurements. It's something that is very a la mode. And so in the ex situ modality, of course, you know the voltage profile. This is the charging curve of a battery that is a pouch cell that has been here connected with a cable. And ex situ modality means that the experiment is taken just with electromaterial a different state of charge. So I measure this, then I open up the cell, measure this, then another cell, I stop the voltage here, another cell stop the voltage here, another cell stop the voltage here. So this is something that you can prepare on your lab. Then you go to synchrotron, and then you have the measurement done. So this is what we call ex situ methods, of course. And operando means that the cell, on the other hand, is connected with the cable to the galvanostat for a charge time cycle. What you have it's very, impressive what the difference are, for instance, in this material. This is a copper nitroprusside, I think, yes, at the copper KH, and we're going to see just an example later on, where you see a lot of not only shifts, so maybe, but also some very difference in some pre-edge features and also in the full X-Annex range. Sometimes you can also you complement this experiment with also the FT calculation on here described. The figure here, this figure, show that this is a bug cell. Okay, this is a diffraction experiment actually, where I don't see it's properly possible. Here is placed a coin cell, and also a detector just is placed behind that is a CC camera. Okay, just behind that for X-ray diffraction experiment. This is also done in transmission mode. Anyway, operando is, by sum up, provides a more holistic presentation of the reactions behavior found under normal operating conditions. And some other example with the operando experimental cell are here indicated. We already seen this. This is also another cell that is here with a sketch of that cell. This is also, you can see probably better here, the coin cell that normally is drilled with at the center. Here is just it's a transmission geometry. Is of course is a Bragg-Brentano geometry. This is coming from the X-ray beam, and then we have the detector that measure in the theta to theta, so Bragg-Brentano geometry. So, what are the the motivation conducting, of course, such experiment, because that is a requirement, and also XRD on batteries and at the synchrotron. So, first of all, operando provides a realistic representation of reaction behavior under normal operating condition. There are typical drawbacks with operando that is here highlighted, and apart is motivation. What are the other advantages? And one of the advantages that now coming to me is just since the cell continues connected with the potentiostat with the cable, if we remember one of the first slides where we show the X-ray and the matter interaction, there are few phenomenon appears, and so we also produce electrons. Since the cell continues connected with the potentiostat with the cable, any surface electron that has been created by the X-ray beam is suddenly removed from the electron surface. Okay, so we have not potential reducing of again of the material. Now, which is the motivation doing XRD at the synchrotron? Probably one of the most important things, apart of course, the intents of the beam, it's that we are tunable photon energy up to higher energy. So basically, you may have work with an extension of this space that can be probed. This is depends on which your, the crystal, not only the crystallinity, but also the cell size. You can work with different cell size, but also adapting the tunable photon energy. If you have, for instance, when you conduct an experiment in your lab, some problem with the fluorescence data, and here, of course, you basically can tune your photon energy in a way that you don't have any kind of remove any kind of fluorescence content of all the other material that in your sample. And last but not the least, it's also the depth analysis that you can do by varying the energy. Typically, the rule is the more the energy, okay, so the more you are probing, the more the probing depth is higher. About operando XAS, we are going to see an example with the X-ray and with the data analysis. Now, first of all, now move to the second part of this talk. I want to show an example, and especially dedicated sample of course, Prussian blue analysis. Of course, I'm not here the one that to say what is the Prussian blue, but anyway, just to start with something very curious. Prussian blue is a color, of course. First of all, is a color that also been used by this Van Gogh masterpiece, Starry Night. And I have one of my PhDs from China, and you also find something that is, I said that is exactly the same color, but I don't know now the name of this work. Anyway, any suggestion that will be welcome. Okay, from the structural viewpoint, and you know so well that, of course, not all the metal cyanoferrates are a cubic structure, but anyway, most of them they are. And for instance, the one that they're using here, oh, sorry, oops, what is the problem here? Okay. So from the structure viewpoint, partial you know, as cubic structure, and where the two iron occupies vertical position, and they are linked by cyanide. Both sides are typically octahedral, and this is very interesting. And this peculiar structure can be also implemented by varying, of course, M1, M2, and also I saw that you vary a lot this kind of a structure in many ways. But here just we focus on this cubic cell. And for me, metal cyanoferrates, when I started to study when I was a PhD student at Paris, I had this is one of the my first work on the metal cyanoferrates, and I just choosing them because that allowed me as a, let's say, material prototype. I want to check one singular things that we have a singular effect that is called focusing or even super focusing effect. And metal cyanoferrates represented the really model compounds to study this high order multiple scattering contribution that can affect all the X-axis spectrum. And in fact, it has been seen, in the past, this is the first paper, that the X-axis signal associated to this material is enormous. When you have a very large signal, it's a good point, because it's difficult to trade also from the theoretical viewpoint, but then you have a wealth of information that you can extract from the signal. And that was due to the peculiar structure of the metal cyanoferrates, which it was characterized. They are characterized as perfect linear chains, high degeneracy of the chains, and also a close distance between the two metal sides. And we know that, if the cube is about 10 angstrom, the distance, of course, is half, it's about 5 angstrom. So in that case, it can really extend what was, the local coordination probe, the typical nexus. So in metal cyanoferrates can be extended so large, and then the Fourier transformation of this excess from the, for instance, iron side, you can see from here, we have the three peaks. The one is the carbon, the other is nitrogen, the other is the copper. So this is an expected the third peak is very intense, very large. Okay, this is due to the four-body contribution, due to the linear chain of the metal cyanoferrates. Okay, and there are also some other interesting points, is that this kind of analysis, of course, even though it's very dated one, still is one of the most, let's say, fundamental one, because it allows a proper extraction of parameters, such as the distances and also the Barbour-like factor and the coordination numbers. And still is in a good mode. Now, I want to present you some of the studies by just starting, from instance, I don't know, your attention, let's say, on the PBA in batteries was due to this paper, published even probably more than 10 years ago, yes, by this group in California, and where they stated the copper cyanoferrate battery electrodes with a long cycle high power. Okay, there was an ideal attention of batteries on PVA, and since then there's now a lot of people in the world try to use this technology, especially from sodium. There also one let's say company in China started to produce batteries based on this in the Prussian white cathode material. There's also one startup in California for stationary applications, and the one in China is dedicated especially for automotive applications. Anyway, what was the good point? The good point can be seen from here, the cyclability. Because even though the specific capacity is not large, it's very, very low, the capacity. So 40, 50, 60, of course, depend on C. Even the C rate is extremely interesting. This material was capable to perform quite high number 40,000 cycles. So this has motivated a lot of people just to start to look at that. So now I want to present some of the studies. The first, why do you want to use hexagon metal sulfate in batteries? First, because you want to do the identification of the metal electroactivity, okay, information about the electronic information. And the best way to do is looking at operando pre-edge structure, for instance. And basically you conduct a charge-discharge curve, and then you're monitoring what you have on both sides, iron and also copper are here as indicated. And there was a belief that only the iron side was electroactive. This is up to, let's say, 4 years ago. But then a lot of people started to think about, okay, let's try to have a second metal electroactivity in the second metal, because that is very interesting, because it would of course enhance the volumetric energy density of potential batteries. So that's why there was the motivation. We can see from here, that is all indicated the energy in this map. Colors, of course, are referring to the intensity. We can see here that if you those two images like this one, we can put like a mirror like here, another mirror here. We can see a lot of feature changes. So that was the clear indication of electroactivity of both metallic sides. This is coming from information from a pre-edge of both sides. But then, let's see another example. Here the motivation was that try to put another, let's say, electroactive portion on the structure, because, okay, even this very interesting, okay, the structural metal sulforates. We know that anyway, the volumetric energy density is kind of low because there is a lot of void inside, okay? This geolytic channel that we have inside. So it's possible to make someone active. So we ended up to have the copper nitroprusside material. When the copper was electroactive, as here indicated, copper extremely electroactive, as indicated. Iron is also electroactive. It's not shown here, but we proved that it was active. And then another was the NO. And the NO, how to prove the NO, we'll see in the next slide. But here, I want to highlight just the joint approach of both XANES from this and also XRD. The XRD basically indicated that if this is the monoclinic structure or copper nitroprusside, during discharge and charge, we have elongation, contraction, and also the opposite holds true during charge. So we can make a loop of continuous loop on this. What is about the milliampere-hour per gram? Not that much great, but still there's a good sign for electroactivity. The only way in which you want to measure the electroactivity on NO was based by an XPS experiment. And so this is the metal NO. We know that during oxidation, so the charge, we have a band of this NO. And one of the ways was just looking at the binding energy, so XPS experiment. Actually, here, some of your paper helped us a lot, because during, if you consider the powder, this is the formulated electrode. So this is the single powder, this is the electrode. It's very clear that we have two contributions, one to the SiN and one to the NO. But then what happened during cyclic sample, we have some other, signal coming out here. And the identification of the signals was due to one, the band NO, the other with nitrogen interacting with the lithium. And this was due to some of the numbers that we found also in one of your articles. About now the excess and why we want to also not only investigate the XANES portion, but also one important to investigate also the excess portion. We can see from this graph. I tried just to summarize. There's a lot of maybe incomprehensible things, but just to focus on two things. The one is allows also the evaluation of the structural disorder induced by lithiation. This is something that you can do, I mean, with the excess-deep overlap factor. This is kind of similar that we have in XRD, but not exactly the same. But if you plot for a different, let's say, during the lithium insertion, if you plot the behavior of those excess-deep overlap factor, we see that, for instance, this iron linked to the excess-deep overlap factor iron C is okay, make some disorder, but not that much. What is very increased in disorder is the copper-nitrogen bond. You can see from this graph that during lithiation, the copper-nitrogen bond has a strong variation on the structural disorder. The other fact is, because of that superfocusing effect, we were also able to try to check. That was very difficult exercise, actually. The number of chains, actually we found that these copper, nitrogen, carbon, iron chains during the lithium insertion, they were kind of modified. So probably we don't have the proof by looking at the oxygen, the water oxygen, residual oxygen that we have inside. But anyway, we was able to just check the number of chains of the copper, nitrogen, carbon, and the iron that is changed during lithiation. Probably today, one of the most interesting aspects that we have on the metal cyanoferrates is due to the manganese. The manganese cyanoferrates is very interesting because we can see that you're going to see that the capacity, the specific capacity is residual capacity is very high, and here indicated. So the following, this is the electrochemical behavior on the lithium ion half cell and on the sodium ion half cell. First of all, it's very interesting plateau. The plateau is very, straightforward, such as in the case of lithium iron phosphate, for instance. And it was important because the manganese is very abundant, iron is very abundant in the earth. So, and we were interested in a complete understanding of the electrochemical systems to explore all the electroactivity of the metal and the structural modifications. And one of the problems was the capacity fading. So, of course, a characterization required, not only in the first, but also on the second, third, and in aging electron as well. So we adopted, as usual, a multi-technique approach. First is to check the metal electroactivity of the manganese. And the manganese is a dramatic changes. It's really incredible, the changes that we have with the manganese. On the iron, basically, there is just a shift towards oxidation and reduction, and that's it. And so we ended up from these figures that both are electroactive. But then, by excess, we were able also to add a piece of information, because they had a strong variation on manganese side to do Jahn-Teller. And we know that manganese 3+ also, it's a Jahn-Teller active, so it's something that could have expected. Anyway, we were able to just identify what is the local geometry changes. So this is basically the figure of manganese 06 as 2.18 angstrom. The manganese, it's a nitrogen, the first cell distance. This is an error. And then it changes from this very ordered picture, because it's a fantastic octahedron, to basically this elongated. So it's, of course, is due to the Jahn-Teller. So basically the two apical distance retains at 0.18, and there is a lot of shrinking on the one of the equatorial plane. So this is during charge and discharge, charge and discharge. This is a huge variation anyway in the first shell contribution. And now the question was whether this extended structure followed the same behavior in terms of elongation and contraction. Because we have to keep in mind that the difference in 10% variation from this to this, it's just locally. So the question is very relevant, and then we just build up a parallel paradox for the experiment. And the parallel experiment has indicated that, interesting, the cell volume changes on only 2%. And we have, of course, no secondary phases detected. Precise lattice parameter evolution on ion exchange are here indicated. But what is important is the cell volume changes only about 2%. So that was very interesting. So we concluded that a non-cooperative Ion-Teller effect is taking place. And this is non-cooperative Ion-Teller effect. And this strong local structure distortion were mitigated by the periodic extended structure. And that's why the capacity fading maybe is not that much dramatic in the case of the sodium batteries. And I want just to skip this, and then I want just to go to measure. Since we were interesting this manganese has a sign-of-rate, we were also interested in conducting some microscopical experiment. And one of the techniques is adopting is a full field transmission soft X-ray microscopy that it was able to give, let's say, a full picture at the nanometer scale, so a nanometer scale of the chemical states and the spatial distribution elements inside the manganese as a sign-of-rate. This paper had just been just accepted. And why doing transmission X-ray microscopy? Because of course you can do with the TEM. While with the TEM you have an electron beam that is very destructive to the material. So we adopted this X-ray microscopy at the synchrotron, especially because of that. Of course, the spatial resolution in this experiment is not as attainable as in electron microscopy, because of course X-rays can be have difficulty. I mean, an electron beam can be more finely tuned respect to an X-ray beam. Another, anyway, view of the microscopy was this one. Sorry, okay. And okay, no, this is just what is the information that you can get from TXM. If we, of course, we need to have a lot of data treatment. I won't be tedious in here, but basically when you get the images with the highlighted homogeneities, different color here means different homogeneities. The very difficult things here is to produce an image in this from this point, because of course you have to normalize, you have to, because the thickness is not exactly the same in all the particles, then you have to find a way to normalization that you have a lot of data treatment in order to get rid of those eventually pitfalls due to just different thickness in your samples. And here was anyway possible to see that samples on aged electrodes, this is case of aged electrodes, do not oxidize or reduce homogeneously through the whole electrodes, but there are differences. Another techniques that is complementary to the other one in terms of spatial resolution is this one. You can conduct X-ray fluorescence spectroscopy with the microscopic things. And why you want to do this? Because first, you have a lot of the sample representativity is, of course, better than in XTM. In XTM, you can have very large experimental, anyway, spatial resolution, as it indicated, but then you just, the portion of the material, just only a few drops that you put in the, you try to do. On the XRF, what is the positives is the sample representativity is very high. And we can see here, or probably, okay, let's just see on this. By tuning your edge energy, your energy of the beam, the primary beam in different way, you can just use a sensitivity of the Xanes for different oxidation state, and then by tuning this energy beam, one here, we have two different maps. So basically, we ended up to have a charge state heterogeneity inside the manganese cyanoferrate cathode material that you can explore by just using a beneficial way of use of the synchrotron radiation. Now, I want just to show you, and this is just one of the last. It's in operando access data, probably we are kind of aware that we have a lot of anyway data. And sometimes it's not useful to analyze all of them. And then we can see that by applying an operando access experiment, we can use the beneficial use of the chemometric approach for data analysis. Some extra information can be also revealed. And we start from the experimental matrix. This is the experimental matrix. This can be thought as a product between the concentration profile per pure spectra. Then, of course, we have an error. Sorry? Okay, yeah. I'm going to finish. In 5 minutes, I will. No problem. Okay. So basically, the outcome is this concentration profile and the pure spectra. So, and you're going to just why we use this algorithm. Basically, this algorithm was, let's say, used by this guy, Romain Tauler. He was a chromatographic man, and then I was interested in recovered response profile of pure components in aerosol and nano mixture. So we tried to adopt for the first time this MSCR ALS on batteries that we produced the first paper. So this is the paper and my group that used this algorithm for the excess analysis on battery data set. Basically, what we got here, we got that if you consider the full data set, by adapting, we were able to see this the concentration profile has been indicated. Of course, you have a spectrum number as a form of concentrations. And we were able to see that actually this data sets comprises 3 types of standards, pure spectra. One is the first, that of course is long-lived. Then we have the second one that popping up, and then is just go down. Then we have the third one. So basically, we were able to identify, let's say, what is the, let's say, transition state by fully charging batteries. You not only have, phase 1, the initial one, that transformed to the phase 3, but also we were able to see just a second phase that was long-living. Then, if you just point, and you're going to analyze from the excess viewpoint only this spectrum, you ended up to have a figure, very precise figure of the copper oxygen. This is what we have, the copper oxygen for resistance, 1.89. This is the coordination number. But now, what we do is, it's kind of standard for us when you have the chemometric, when you have some operando access data, we have this chemometric approach. And this is, for instance, an example that we have on a manganese KH and the iron KH on the manganese cyanoferrate sample. We can see from here, from this plot, that at the beginning, we have just the 2 spectra. So the first, then we have a conversion from this species to the other one during the charge, and also the opposite all true during this charge. So we have basically 2 components, one component is true, one transformed to the other. But what's very interesting that this is the manganese KH. If you see the plot of the iron KH, we were able to identify that at the iron KH, we have also something that popping up here. That was due to the fact that we have hydrated samples. Okay, so probably we have a transformation from hydrated to the dehydrated one, and then we have the charge distance phenomenon. And the same was also true with this iron as a son of cobaltate operando data. Well, I'm going to the conclusion here. We started with the X-ray, the couple of techniques we adopted with the PBA. We use this with the battery materials, and when we want to explore how to analyze well the data, of course, we had the beneficial approach using the chemometrics techniques. So I'm done. I want just to say thanks to all of you for the kind attention. Thanks for my groups that here indicated. That is now some people have changed, but anyway, thanks a lot to you for your kind attention.
Professor, if you agree, we'll continue with some questions from our audience.
Yes, of course.
Good afternoon for you, Professor Giorgetti.
Yes.
Today I was wondering what took you to use these materials for batteries, I mean Prussian blue analogs and nitroprosides at first. What took you to use them?
Sorry, and was not that much clear, but anyway, I try to. So you're asking which kind of material could be used in the batteries on the Prussian analogs on which cells?
No. What reason
Sorry.
took you to use these kind of materials, I mean Prussian blue analogs and nitroprosides in batteries?
Sorry, probably I really had hard time to understand. I'm sorry. Could you please repeat the question?
Yes. What took you? What was the reason?
What was the reason?
Yes.
Okay, but the reason was, you remember the reason was this? Okay. Apart is now the reason is very well documented by this, for instance, behavior, okay, of them like here. The specific part is reached 130, 140, but this plateau is very high. Plateau is 3.5. It's very interesting in a way. Of course, it doesn't reach from the lithium of the sodium, the plateau of, for instance, element O, element the iron phosphate. But the specific fat is extremely high, okay? And especially there is a lot of improvement in this capacity respect to the first paper you try to use this material in batteries. You remember that number there was about 50 milliampere hour per gram. Here we reach almost 130 milliampere hour per gram. And then it seems that this study also showed that there is a trajectory that you can follow in order to improve those cathodes. I mean, mitigating the Jahn-Teller effect on this, it's a solution to have some very well performant cathode material, okay?
Yes.
That was the
thank you.
motivation.
Yes, thank you so much.
Another question? I will take the time to say that it was really nice to see the bending of nitrosyl group because I mean, I like coordination chemistry, and you know that we can identify just when it is fixed in fixed positions, this group, and you showed some experiment where you can follow the bending, right?
Mm-hmm. Yes. The next, yes. Yo, that one was, I mean, the paper about the group, maybe your group, was very, because what we are missing here standards, of course. In XPS, you need the standards. And then what we need is a standard of a nitroprosate, but which do you have inside, what you need is really a standard for manganese sulfate, basically. Okay. And that was, I was scrutinizing all the papers, and then they were just find, I mean, some of your paper that me just the chance to look at them. Yeah, it's something that is really happening with this NO.
Yeah.
Because I mean, as I said, Prussian blues are open structures. They are very nice, and especially this. Sometimes we can also call them such as low strain materials. Low strain material means that you can adapt. I mean, the structures very easily because you can accommodate in this fast reaction, insertion or insertion reactions. Okay, and this is one point on the one end. On the other hand, you have to make all the metals, all the chemistry that inside, you try to have electroactivity on those ones. That's why we try to approach this NO. And that XPS spectrum was the only techniques that he had just to try to have a response on if it's that true or not that you have this band of NO. Another was the frequency was the IR actually. Mm-hmm. And then he also had, not shown here, some IR in operando way. And then that one also, the change in the frequency, the IR, was also a digital, let's say, fingerprint of what was happening. I
can imagine. And well, I enjoyed a lot your work, what you have shown. I think that it is magical, this in operando systems, because we have just imagination when we don't have all these tools. How do you say?
Yeah. Okay. I hope that anyway, the next week or anyway, kind of. Was a kind of the first, let's say, meeting. I was really glad that of your invitation, and I hope that we have got the chance to talk. I mean, the next days about, I mean, future anyway collaboration that we had with Edilso. We also that when COVID happened, and then that was very bad for everyone. And then we tried to set because also this is I can show you probably something that you know well, Edilso. This is the Advanced Spectroscopy in Chemistry Master Program. And so still we run this master. And I would like to, anyway, to use also this master in order to invite you or some of your colleagues in here, anyway, for a couple of weeks, okay? We can do that in order to try to strengthen this collaboration. I'm interested in metal isosonography rates. If you're interested also in this kind of techniques that you can try to have together here, I will be glad that we can have a cooperative approach.
Great, we would love it. We have an auditorium, plenty of students here, and so we welcome your invitation, Professor Giorgetti.
Okay,
any other
perfect.
Question, please? Yeah, another question.
Yeah, thanks, Professor, for your lecture. It was very interesting. I was wondering, which are the biggest challenge when you are studying the insertion of ions as lithium and sodium, which are very small by XRD, by X-ray diffraction?
By XRD, okay.
Yeah.
Okay, in let's say if you go to synchrotron,
yeah,
if you have a very crystalline material, sometimes when you do Ritfield, you can also try to analyze the deposition, okay? So you can have a clue. But especially on sodium, because lithium, I mean, as you know, it's very difficult to check the position of the lithium. Anyway, even though if you go to the synchrotron, you have this measurement with the high resolution measurements, this is something that you can do. But what I can say is that, yes, it's sometimes it will be possible, especially on the sodium. So you can just try to finalize also the atomic position for sodium. It could be possible, but just the sodium.
Okay, thanks very much.
Sure.
Any other?
Thank you, Doctor. I have another question, please. You focus your work using PVAs as cathodic materials, that's right?
Yes.
But recently it has been published the use of these materials as solid electrolytes for specifically sodium batteries. Do you think it's a good approach to be focused on using these kind of techniques for the study of these materials?
Yes, you can adopt, of course, to design a particular experiment also to do that. Yes. Yes, why not? Of course, the design of the experiment is one of the most problematic things, maybe. even with the cell that we have to adapt. But when you have a focus, you can try to to model what is your anyway electrochemical apparatus in order to have them working also in some other conditions.
But do you,
So,
do you have
but we have to
the intention?
be.
Sorry, to do that?
Sorry, I didn't get it, that one.
I mean, do you have the intention to study these materials with this approach?
Okay, okay, not now. Which material we refer to? The vanadium? We saw the vanadium.
Okay, thank you, doctor.
No, sorry, because I see. I sometimes I really heard some only metallic voice and that's it. So I sound in my ear just metallic sound I heard from that.
No, I mean, my question was, if you have the intention of focusing on this approach in your research team, using PBAs as electrolytes, not just cathodic materials.
Yeah, the electrolyte is not now anyway.
Okay.
We try to okay. For instance, someone also uses as an anode. As an anode, you may have vanadium. You have to go to cobalt, but first cobalt is impossible. Of course, is very all the battery community try to get rid of cobalt, as you know so well. So cobalt is not possible. Vanadium, what would be the beneficial of using vanadium? Vanadium, it's probably at 1.3, 1.5 volts respect to lithium. This means that if you combine this vanadium anode with something that you work as a 4, you end up to have the battery just on 2.5 volt. That is not probably good. So I think one of the most interesting things of the application of PBA in batteries is really the cyclability, and probably the solution is just a stationary application, just for stationary batteries, okay? So batteries that even though the volumetric energy density is not high, battery for load leveling on the stationary application. I mean, I see probably the future just on that application now. Maybe the manganese is also interesting because 140 milliamp per hour per gram is interesting, of course, but it's difficult to sell this technology to a company interesting, but then you have to say to the company, hey, pay attention because this Yanteller effect could maybe in the long term, let's say, put in jeopardy all your battery. So it's very difficult, okay? So I really see probably some things related to only the stationary applications.
Okay, I understand. Thank you.
Sure.
Thank you. We still have another. No, I don't think so. So let's thank again Professor Giorgetti, and it has been a pleasure to hear from you and your beautiful work, Professor. Thanks a lot.
Thanks a lot. Thanks a lot to you, and have a nice day and also evening, okay? And then we'll keep in touch. My wife just said adios because my wife actually speaks Spanish because she's a Spanish teacher, so probably it could have been. Okay. Okay. Bye bye.